I want you to think about this circuit for just a minute. And although we're going to look at an RC today, we're going to look at RCs in two different lights. This is the first light. And we're going to change this in just a minute. But let's go 3 ohms, 3 ohms, 18 volts, and 6 microfarads. All right, everybody see the circuit okay? Let me turn out the lights. You guys in the back? You got it? Thanks, that'd be fantastic. Now, I can't prove this for you yet, but we're gonna have to find a way to prove this soon. But right now, there's no current in this system. This has to be true because there's a capacitor in the system. And because there's a capacitor in the system, there can't be any current flow past the capacitor or the capacitor has failed. So if I were to draw a single loop to describe this circuit, at the present time, this would be the only loop I could draw. With the switch open, this is the only pathway for charges. Now, if I tried to use Kirchhoff's laws to describe this loop, what would be the voltage across the resistor? I mean, we could say that there's the 18 volts minus the voltage across the resistor minus the voltage across the capacitor. I mean, we can set that equal to 0. And we can substitute in what we know about voltage for resistors and voltages for currents. The voltage for a resistor is IR, and the voltage across a capacitor is going to be Q over C. If there's no current, there is no voltage across the resistor. When I set up this circuit and it operates, all the voltage will be across the capacitor, and the capacitor will be charged. This is known as the steady state condition. In the steady state condition, we evaluate the circuit the same way we normally would, but we have to keep in mind that current can't pass through a capacitor. So our circuit treats the capacitor as an open line, meaning like a switch. But that doesn't mean that the circuit doesn't perform, meaning I have a charged capacitor due to this circuit. Now, knowing that this is going to be 0 because there's no current is really just a cop-out, because there had to be a time in which that capacitor was not charged. Maybe a time when I first set up the circuit and had a switch here. And at that moment, the capacitor wasn't charged, and then I closed the switch. That meant the capacitor had to go from being uncharged to now being charged, which meant there had to be a time when there was a current in this circuit. In fact, if you think about time 0 being the instant the switch was closed, I want you to think about this for a moment. Time 0 is the instant the switch is closed. What would the charge have been across the capacitor the instant the switch was closed? I'm not trying to fool you. Was the capacitor charged before being connected to the circuit? So at the instant the switch is closed, at time 0, the capacitor had 0 charge, which meant at time 0, there had to be some amount of current in the circuit. There had to be. There had to be a way for the charges to get to the capacitor. So when I first close switch A, there must be a current. That current doesn't last very long because the capacitor is there. So the moment the capacitor is charged, that current goes away. And then there's no current at all. That's considered the initial state. So there's the initial state, and then there's the steady state condition. Capacitor circuits transition from an initial state to a steady state condition. The steady state condition is what happens after a long period of time has passed. Don't be fooled though, long period of time in circuits can be milliseconds. But we consider the steady state condition to be the long-term condition of the problem. The initial condition assumes generally that you're just closing the switch. If the capacitor is charged, you have to be told, otherwise it's assumed that it's uncharged. Now, this has several implications. The first implication is that at time 0, and these are things I would know, when switch A is closed, time 0, at that moment, the voltage across the resistor is going to be 18 volts, which also suggests then at time 0, the current through the resistor is going to be 6 amps. Then the steady state takes over. In the steady state, the voltage across the resistor is 0, current is 0. At that time, the voltage across the capacitor is 18 volts. Which means the charge on the capacitor is going to be 6 times 18 microcoulombs. I don't know what that is. What is it? Now, I want to continue this discussion because we have switch B here. Switch B is going to change the circumstance and add a complication, I hope you realize. Because the moment switch B is closed, the capacitor has an 18-volt potential difference. But after the switch is closed, we have a complete pathway, which is going to allow current to flow in our circuit. You guys see that too, right? So the initial closing of our switch is probably going to be complicated. There's energy in the capacitor and voltage across that capacitor, which is not going to stay the same in the long term. In the long term, when that switch is closed, we're going to have current that passes through the circuit and not through the capacitor. Can you all kind of look and see what's going to happen in the long term? When I look at the long term, I see this loop as the only loop with current. And in that loop, there'll be 2 voltage drops, one across each resistor. In that loop, the total resistance is 6 ohms, which generates a current of 3 amps. I think in the long term, we're going to have voltage minus voltage across one resistor minus voltage across the other resistor, and that's going to equal 0. And that likely is going to make a current of 3 amps and a voltage drop across each resistor of 9 volts. What do you think the voltage across the capacitor is going to become? Kyle? I don't think it's going to be 0. I think it's going to be 9 volts. By Kirchhoff's laws, once I reach that steady state condition, this loop has to also obey Kirchhoff's law. And if there's 9 volts of potential difference across this resistor, that means there must be 9 volts of potential difference across this capacitor in order to obey Kirchhoff's laws. Which of course suggests that there was a time when that capacitor was at 18 volts and had to transition down to 9 volts, discharging its energy probably through the resistors of the circuit. Because I'm assuming now it has less energy since there's less voltage. Yes, sir.
So does that mean that the resistors would have a higher power output than the capacitor?
That's an excellent question, isn't it? There's going to be a fluctuation in the power readings of these capacitors, of these resistors, while capacitors are charging and discharging. That's exactly what's going to happen. And what's important to recognize here is that we in this class don't get to take that for granted. We have to figure that out. We should be able to figure it out. And the reason why is because we know the definition of current isn't necessarily based on an idea of a constant. Our definition of current is based on the fact that it's a derivative, it's a rate. We should be able to develop a function for the current in this circuit that describes the rate at which the current changes, and therefore the rate at which these capacitors charge and discharge. Now, before we launch into the mathematics of this, which we're going to do today, this is solid mathematics, good stuff. Be prepared for stuff you've seen and some stuff you haven't seen. But more importantly, once you've done this once, you've done it for every kind of RC circuit there is. So this doesn't change when we go to other circuits. So the mathematics of an RC circuit is pretty fixed. And even if you make the circuit more complicated, rest assured, all circuits are an equivalent capacitance and equivalent resistance. So they can all be boiled down to the RC circuit. One resistor, one capacitor. That's what we're going to base as our model. And we're going to use that model to come up with the charging time and the discharging time. Okay, so that's what we want today. I want to create a function for the current based on time. This should also allow me to have a function for charge on a capacitor based on time, and a function for voltage across a resistor based on time. I should be able to derive all of those. More importantly, I hope you recognize that if this circuit has some kind of transition from having current to not having current, this has a function then, right? We can use this circuit to time things. It might not sound like much, but I want you to think about this in your whole mantra of things you know about. My new computer is switching on and off in the gigahertz frequency, right? We all have heard this before, that processors have a frequency, maybe 3 gigahertz processor. Have you heard that phrase before? Even a little bit when it comes to computers, I hope. That's saying that there's 3 times 10 to the 6th on and offs of your computer every second. Something has to cause that processor to switch on and off 3 times 10 to the 6th times per second. It is an RC circuit timed specifically to function as the gatekeeper to switch your computers on and off that many times per second. That's how processors work. A processor chugs out an answer once every time it's flipped, every time it's turned on and off. So what you do as a computer manufacturer is you find a way to turn that processor on and off lots of times a second. And every time you turn it on and off, it sends you an answer. It's doing whatever you're asking it to do with those numbers. Now that's an oversimplification, but it is exactly what those processes are doing at the fundamental level. We said we were going to talk about that and do a little bit of that from now and again. That's going to be, actually we're going to spend like the last 3 days of school this semester doing nothing but digital logic stuff. So we'll test on this next week, and then we have 3 days of logic. It'll be kind of fun. So let's do this though. This is my this is some of the best stuff we do, I think, in circuits because we get to leave the realm of boring old, here's resistors, reduce them down, and these are more interesting. They can do things. We're going to do a single loop circuit, and this is going to be all theoretical. So I'm not going to use a V. I'm going to use the script EMF. That's traditional here, because that way I don't get it confused with the fact that I'm going to have a V across the resistor and a V across the capacitor. We do need to have a switch because we're going to talk about two different parts of this circuit. We're going to talk about the charging of the circuit, which is probably all we'll get to do today. But eventually we should put another little line in here and deal with the discharging of the circuit. So we'll discharge the circuit though, probably tomorrow. I don't think we'll have enough time to do all of it today. So we're going to assume that the switch is closed, and we're going to call that T equals 0. And at T equals 0, we're going to have some boundary conditions. At T equals 0, we're going to say that our capacitor has a charge of 0. So it's an uncharged capacitor put in series with a resistor. And at time 0, we're going to close the switch. It's a single loop. So whatever the current is in the circuit, the current should be the same everywhere. And based on Kirchhoff's laws, we should be able to say that at time 0, we get a single loop describing the voltage drops across the capacitor and the resistor. Now, what we're going to do next is pretty straightforward. We're going to substitute in Ohm's law for our resistor, with R being the value of the resistance. And we're going to substitute in Q over C for the capacitor, with C being the value of the capacitance. We're set that equal to 0. I'm purposely using lowercase q and lowercase I to represent the fact that these are transitioning variables that are not constants. And this is our Kirchhoff's equation, but our next step, and what you'll be asked to do on the test, is to create a differential equation that could be used to solve for the current in the circuit, or to solve for the charge in the circuit. For us, we're going to solve for the charge in the circuit first, because our differential, as you guys know, is dq dt. This is how we create a differential equation. So wherever I see I, I'm going to drop in dq dt. Now we have created a differential equation that could be used to solve for the function of q. I'm sorry, solve for q as a function of t, which is what I'd really like to do next. Now, for you guys who are in BC, this should be close to your wheelhouse. It might be a little tough. You guys are in AB, this is outside of it. You need to learn how to do this. So we're going to do all the things that we talked about before. And I'm going to need more room than this to work. So you're probably good with me going to another page, I think. So the first thing I want you to do is separation of variables. So let's start by isolating dq dt. Now, here's where it's going to get a little bit tricky. I think you probably can see it coming. First, I need to get, separation of variables requires I get, dq on one side, dt on the other. And when I do that, I've separated my differential, but I have q on the other side. So I need to move q to the right side of the function. So Now we have something to which we could find the derivative. Now, this is pretty ugly. So there are some things that we can do to clean it up a little bit, but there's really not a whole lot. One of the things that is sometimes done is to put the R in the denominator. That can make it look a little cleaner, but there's really not a whole lot to do here. So just for aesthetics, I'm going to move the R to the other side of the function. So I have less here. Since the other side of the function is just dt, it's a little less complicated then. But that's all I can really do. Now, you guys understand that the next step is to take the integral of both sides. And when I take the integral of both sides, I want to set my limits. So we have some limits. We're starting at time 0 and charge 0. And we're looking at some future time when the capacitor has some future charge on it. Those are our limits. Any questions so far? All right. So the left side isn't the problem, right? It's the right side that's the issue. And in order to do the right side, we're going to have to do some form of more advanced calculus. We're going to do U sub. U sub works here pretty well. So to do U sub, my U is going to be all of that. And take the derivative of that with respect to Q. The EMF is a constant, so it just goes away. And I'm left with minus 1 over C. Questions about that? I'm going to solve that for dq. And I'll get negative C du. And now I have two things that I can substitute. We all okay with that too? All right, so let's make those substitutions. I don't know why I put the parentheses like I did, so let me clean that up a little bit, make it look nicer. Ugh, I know it's messy. It'll be okay. I'm going to pull the negative C out if you don't mind, but I'm going to do something that you won't expect. And it's not because I'm trying to trick you. It's just because it's customary to kind of collect the variables. So I'm just going to divide both sides by the negative C and put all the constants together on one side. Is that okay with you guys? Often, actually, this is written in the other order, R times C. That part doesn't really matter, but I'm just getting all the things together. Because now I have two relatively simple derivatives to which I can figure out their antiderivative. Meaning this side is known to me to be the natural log. And the other side is known to me to be t. Now, truth is, I have to do something here that, you guys should expect. I have to U sub back in my original function and then apply my original limits. But I'm kind of out of room here. So do you mind terribly if I make some room? Is that okay? So let's do our substitution. Trying to go nice and slow. I put my limits in already on the left, but I have to put my limits in on the right now. Everything okay? Trying to go nice and slow. I'm gonna go to the next step. We all good? No worries. All right, so here's where you might, have some issues. I want to get rid of the natural log. So I'm going to raise both sides to a base of e. And that makes this e to the minus t over rc. And this side becomes doing good so far? I want to separate this fraction. And I think it makes sense as to why. So when I separate this fraction, I get 1 minus q over EMF times c. Remember, our hope is to derive a function for q. So I want to solve this for q. And this gets me one step closer to solving it for q. But of course, we have like run out of space again. So I know it's a lot, but let's go ahead and keep going. I'm going to put q over this on this side, that on the other side. And now I just got to multiply both sides by EMF times c. This is the charging function. Now, there's a lot I want to talk about here, and it was a long way to get here. And you should look at your notes and have all those steps in there because it's the same no matter what. This is a charging circuit. And this is what you get at the end of a charging circuit. Believe it or not, we haven't done it yet because we're waiting because mechanics is a different animal. But this is also the exact same thing you get when you deal with an object in linear drag. Same function. So if you do the linear drag function, you'll get this. These things show up all the time. This is the first order differential equation with respect to a single variable t. It always produces the same answer, an exponential climb to an asymptote. That's what this is. I don't know if you see it as for what it is, but think about the terms for just a minute. When time equals 0, so at t equals 0, what is this term going to be when t is 0? Think it through all the way, it's going to have to be 1, right? E to the 0 is 1. So at t equals 0, what is all of this going to be? So at time 0, the charge in the capacitor is 0. Of course it is. That was our fundamental starting point. Our function has to produce that. But look at the other side of this. What about when we go t to infinity? What does this term do as t goes to infinity? Yeah, it approaches 0, gets very, very small, or approaches 0. Which means that at t equals infinity, q equals, now look close at what this is. Do you know what this is? It's what you would get if you just attach the power directly to the capacitor, right? This is the maximum charge in the capacitor. Because this is just That's exactly what we said would happen. It's exactly what we expected to happen. Which means that in this circuit, and this shouldn't be a big surprise, if we were to take and make a plot of Q as a function of T, we would get an asymptotic approach to Q max. I'm going to need you to be able to make these kinds of judgments. I'm going to need you to be able to do this kind of derivation. Now, there's more to it than this. How you feeling right now at this point? Not so bad, I hope. It's a little, there's some stuff here. I agree. There's some stuff. Yes, sir.
Doesn't that kind of imply that it's never going to be fully charged?
That totally implies that's never going to be fully charged. Totally implies it. And that's just it. We would expect that in any of our circuits, the capacitors never go to full charge because at the end, they're all just trickling in at the top. Now, here are some of the things you have to recognize though. First, this is all controlled by this. You understand that this determines how long it takes for these things to happen. This is often called the time constant. It has to have units of time. Don't know if you realize this, but that means if you take the product of ohms times farads and work all the units out, it has to be seconds. Now, you should do that. Mostly because I don't want to. I have to have to remember what a farad is and what an ohm is, but you should do it. Because to me, it's amazing that in all of this, RC equaled seconds. But also RC sets the timing. If RC is bigger, this circuit takes longer to charge, which means you can adjust how long it takes for your circuit to charge up by adjusting one or both of these. It's a timing circuit. You've decided. Now, I want to do more than just this. This is not where I want to end, but I have to make sure you understand that once you know this, you can also just memorize this. This is not on the formula sheet. It's worth committing to memory. All charging cycles are going to look like this. All of them are going to. They're all going to have this 1 minus exponential. They have to. This is where the exponential really comes from. And there's more to just memorizing this, but if you can memorize this one and the discharge one, you can derive everything else. Not that you really have time to derive on the test. Because the very next thing I would like you to be able to do is figure out the current in the circuit. That should be what you do next. And this is an all skate in that no matter what calculus class you're in, you should be able to take a derivative, even if you can't do an integral, no matter how complicated that derivative might be. Everything there is a constant except for t. My expectation is that you could come in tomorrow with a function for function for current as a function of t by taking this derivative. It shouldn't surprise you. We already said that current drops to 0 over time. We are expecting the current function to start and drop to 0. Prove it. You're not going to be surprised at what you get for the max current. All right, that's it for today. Hope that was good. Have a great day today. See most of you for some fun times at